Welcome to Total Network Operations, the project with a podcast dedicated to hardworking network operators like you who deliver all the packets, all the messages, all the datagrams, all the segments, and all the PDUs. We have conversations with operators and vendors about their great ideas in NetOps so you can make informed decisions for your network and your team and to spur constructive dialogue between vendors, NetOps teams, and across the whole NetOps community. I'm your host, Scott Robon. Today, we have an extremely special guest with us, a gentleman named Jack Haverty. Jack is a veteran of early ARPANET operations and innovation. What do you do when you don't have the tools you need? Well, you create them, of course. And Jack has done more than his fair share of that. His journey has taken him through MIT, BBN, Oracle, and many, many points in between. He didn't just have a front row seat in the early days of packet switching. He was on the playing field. And he may have actually been the first ISP. We'll talk about that in a little bit. He's contributed so much to what we rely on and take for granted today. Things like the first Unix implementation of TCP, and we'll hear about that and so much more. So Jack, thank you so much for being here and being so generous with your time. Why don't you give your own more extended introduction, what drew you to networking, how you got involved in ARPANET and more, and start with like your technical curiosity. Like I'm sure you didn't start right in networking. You probably started in computer science. What's your superhero origin story?
Well, thanks, Scott. My interaction or my interest in communication stuff actually started when I was in high school, and I got into ham radio and got a radio license and all that. So I got into passing messages across the radio waves and so on, and that was pretty interesting. And I remember I talked to a guidance counselor of some kind way back then, and he said, "What do you want to do?" The standard question: "What do you want to do with your life?"
Right.
And my answer was something like, "I want to build things that people use." So that was sort of the beginning of the journey. And to the extent that I was involved with the internet, I guess that qualifies as something that people use.
I think so. I think I can check that box, definitely.
Probably check that box, yeah. I got into MIT as an undergraduate and went through the four years of fire hose education there.
Wow.
But when I was due to graduate, I got into a 5-year program to get a master's and bachelor's combined. And that's when I met Professor Licklider.
Okay.
Our Licklider everyone called him Lick. And I ended up spending the next probably 8 years at MIT in Lick's group, first as one of his thesis students. And then I became part of the DSR staff, part of the research staff. So
DSR, can you, what is DSR?
DSR is Division of Sponsored Research.
Okay.
So it was the research projects that were funded by the government, which is basically everything that was being done.
Sure.
So we got to do not only the fun stuff, but also the things like pulling up the raised floor in the computer room and running cables underneath it. And,
sure.
Being on staff, you got to do the grunt work too.
Right.
But Lick had this vision that I guess I got indoctrinated into. And the vision was of the intergalactic network. And the intergalactic network, he actually wrote about in 1960 or so. And then the notion was that it was computers all over the place so that every person would have his own personal machine of some kind. At the time then, it was a terminal attached to some big mainframe somewhere.
Sure.
But everybody would be using a computer, and all of the computers would be somehow connected together to form this intergalactic network that helped people do everything people do. So it wasn't limited to email or browsing the web, or the web didn't exist back then, of course, but it was just being able to use computers to help people do everything that people do. That was his vision, and we struggled for years implementing parts of that. People have to understand that at the time, the world of computing was quite different. I mean, most computers would not fit in a building. They were huge, they were expensive, and they were really slow.
Right.
one megabit per second was considered a fast machine. Now we're talking about gigabits and multi-cores and whatever.
Yep.
There was never enough memory. 32 kilowords of memory was huge. Now we unless we have a terabyte, we think it's crazy to even try it. So the world back then was highly constrained, but the vision was still there. The vision was that eventually people would have enough computer power that they could have their computer do something for them, and it would talk to all the other computers around to accomplish that. That's pretty much when I look back at it today in 2025, that's pretty much what the web internet is today. It's the thing people use to do everything that you can think of.
Yep.
So going on from that, I worked on a lot of projects there. Mostly I worked on electronic mail. Lick was a big proponent of the ARPANET and the interconnected computers kind of thing. So he actually was one of the people who started ARPA, Information Processing Techniques Office, which is where all that work came out later. He came back to MIT and ran the group that I was in. So at that point in time, we started working on things like electronic mail, which was viewed as not so much electronic mail, but computer-assisted human communications. There was an organization called CACOM, which is CAHCOM, Computer-Assisted Human Communications. And the task of that group was to figure out how to use computers to help people communicate better.
And does this goes back, just to maybe tease this out a little bit, Lick's background was psychiatry, wasn't it? He was not originally a computer scientist. Yeah.
Right. He was basically a psychiatrist. So he understood the people side of things.
Sure.
He understood technology, but he was never really that much into technology. He didn't sit there and write his own code or that kind of thing. But he made lots of things happen by getting other people like me to do the stuff that he envisioned having done. So we created some of the first electronic mail systems, and there was actually a lot of work done in that never came to fruition because the ideas we had were a little bit further ahead than what most people wanted to do, as most of the people involved around the ARPANET wanted something they could implement, like over the weekend, and not require 6 months of research project.
Right.
So the thing that's called SMTP, Simple Mail Transport Protocol, is actually a simplification of what used to be called the MTP, the Message Transport Protocol, which encompassed a lot more than what we have today. And that's never actually come to pass, the follow-on to that. But when I got involved as a user of the ARPANET in that mode, I was basically writing email programs.
Sure.
Did a bunch of other things. We always liked to use the ARPANET. And when I at one point I decided I had to go into the real world, and I migrated to BBN, which is about a mile or two down the road from MIT.
Okay.
Which is not really going into the real world because BBN was pretty much the same as the MIT world.
But it was a private company, and they did funded research in multiple areas, or largely focused on communications?
It started out as an acoustical research company.
Okay.
And it did. There were still several different branches of the company that did acoustical work and did things like when the Watergate recordings happened, BBN was the one who analyzed the tapes to figure out what went on. Okay. They designed the concert hall for the United Nations. That kind of work. So it was pretty impressive as in an acoustics aspect. Acoustics is what got BBN into computers.
Acoustic couplers for modems?
Well, they use those certainly, but computers were the way you could analyze all this stuff. When you take measurements for concert halls and things, you had to have a way to model what was going to happen in order to fix things. So it had this legacy of the computer used in acoustics. And when the ARPANET I wasn't there at the time because I didn't get there until 1977. But back in 1969, when the ARPANET project was going, BBN bid on it. And if you look at the original proposals that BBN put in at that time, they're very strong on the fact that the design would use a switch which was separate from the computer.
Okay.
And that was called an IMP. It was based on a Honeywell 316 processor. But there are a lot of good reasons for that, and they're all outlined in the documentation or in the proposal that they put in. But it was things like if it's all in one place, then you don't have the load on the mainframe, which everybody charged by the minute of use at the time.
Sure.
So the mainframe was very expensive, and people didn't want to have their computing power used up by this networking thing that was, this newfangled idea that somebody was imposing on them. So there was a lot of that kind of justification for having a separate IMP from the network. Whereas IMP was in the network, and the mainframe or the host computer was not really touched much at all.
And is it appropriate to think of the IMP as basically the first router? I know you use the term switch. It's a packet switch. Yeah.
It was the first router, but maybe I should go into this a little bit now. When TCP occurred, which is jumping ahead a little bit, but when TCP occurred, a thing that happened there in an architectural sense was that a lot of the mechanism that in the ARPANET was inside the IMP itself. For things like flow control and congestion control and routing and all of that stuff inside the ARPANET was basically the mechanism to create a virtual circuit service. So bits you put in one end from a host were guaranteed to come out the other end in order, not duplicated, not lost, perfect.
Right.
It was a wire. It was basically a virtual circuit wire. When TCP happened, the design of that took a lot of that mechanism and put it into the host computers. So instead of having things in the switch, they're now in TCP implementations inside the host machine. When I got into the TCP world, I got into when I first joined BBN, my assignment was to implement TCP on a PDP 1140 Unix system. And I was the perfect choice for the job because I had seen Unix used once by somebody in one of the other labs at MIT. And I remember looking at what was going on and what was being typed and thinking, he just typed in a bunch of gibberish and a bunch more gibberish came out. So I didn't know a whole lot about Unix. I also had never actually written any network switching type code. So I didn't know a whole lot about network code. And I had never worked on an 1140. I'd worked on a PDP-8, which helped, but it was a slightly different machine, but not that different. So obviously, I was the perfect person for this. I had no preconceptions that things would not work because I hadn't had any experience with it. In retrospect, I think that was probably important because since I didn't know things that wouldn't work, I wasn't afraid to try things that might not work.
Valuable. Lack of that exposure, you didn't know where you should stop, so you kept going.
Exactly, and that actually turned out to be one of the principles that ARPA used in its decision making about what to do. I got to talk to a lot of the ARPA guys over the years, and one of them told me that they actually are they get negative points from the management if they don't have enough failures. Because if they don't have enough failures, that means they're not trying things that are advanced. So they have to try things that are not known to work yet.
Right.
So a lot of the things that happened inside the internet world were things that were done not because we knew they would work, but because we didn't know that they would not work. So that's a little scary, but
it's a very useful principle, right? Again, so you don't have a built-in hold yourself back mechanism which is fine for software. They have the hold it back mechanism is useful for not driving a car off a cliff. We would want it there, right?
Yeah.
But not for this realm. So no, that's a great call out.
Yeah. So that's the kind of world that the ARPA projects were done in. And I should back up a bit and go back to MIT for a second. One of the people down the hall from me, in an office down the hall from me, was the one who implemented the IMP interface for our own PDP-10, Licklider's PDP-10. Mm-hmm. You might have heard of him. It was a guy named Bob Metcalf.
Yeah, something about maybe Ethernet, maybe?
Yeah, I think he did something with Ethernet later. That's true. But he was doing his thesis, which was it was at Harvard, and it was on thin wire interprocess communications. So that kind of mentality was inside Lick's group. He was instilling in lots of people the notion of networking and why it was a good idea and how it could possibly change the world and all that kind of stuff. So a lot of the things that happened there, it was an interesting environment because in most research groups at universities, the focus is on writing papers. Because you write the paper and that gets you into the journals, and that's the way you make your mark. Lick's group, I don't remember we ever wrote any papers. There were students came through and they did theses,
sure,
which are in the public world, of course. But the focus we had was writing code. Mm-hmm. So we wrote lots and lots of code, some in assembly language, some in a very high level language we call it muddle. Was Lisp-like, but it was sort of like engineering meets academics. It was a mix of things that had lots of interesting debugging tools. But that mentality was now replicated in the ARPA world. Mm-hmm. And that's how I got involved in writing the Unix TCP. The Unix TCP was interesting because at the time, Unix was pretty closely held by AT&T. It was owned by AT&T.
Right.
So people were worried that if you worked on Unix, the internals of Unix, you had to sign a non-disclosure agreement. And that might make it hard for someone else to hire you in the future because they'd be worried that you'd be taking stuff that you learned in the Unix AT&T world and somehow cross-pollinating it. So there was some cost involved in actually working on the Unix project. And it also meant there was essentially zero documentation about how the kernel worked. And the only thing I found was there was a University of Wollongong in Australia. Somebody there had produced a little book that basically was just a description of how Unix worked inside. And I remember I got the book. I think ARPA sent me the book and said, here, read this. This may help. And that helped a lot in figuring out what was going on inside Unix because it was, I worked on other operating systems and typically you go in and you find things like the memory management module or the scheduler was another big one. I found the scheduler in the Unix system that I was using at the time. Mm-hmm. This was Unix v6. And it was basically maybe 30 lines of code. It wasn't a module. It was just a little chunk of code in the middle of the program.
A very important chunk of code.
Very important chunk of code, but it was not easy to find. And we actually, a couple of us went down to Bell Labs in Holmdel, New Jersey at the time.
Sure.
And met with Dennis Ritchie to get his view on how this was going on, what's the right way to do it and all that kind of stuff.
Of Kernighan and Ritchie and the C programming language, correct?
Exactly. Yep. Well, they were the ones who actually built the first Unix.
Right.
At AT&T, which was another one of those projects that wasn't authorized. It was just kind of like they found this machine lying in the corner and they said, hey, we could put something on it and work that way.
Amazing.
So there's a lot of that kind of mechanism going on underneath the work there. But anyway, I figured out how to put TCP in. We actually, Randy Ripperg and I wrote a paper that we did publish in, I think it was IEEE Transactions on something or other, communications probably, about we had to add 2 new primitives to the system code. One was called await, and the other was called capacity or capac, because there was no way to tell in Unix that we could figure out whether or not who you should wait for in a response, in a request response kind of mode. Was the guy at the other end of the network connection going to send you something, or was the person sitting at the terminal going to send you something next? There was no way to be able to wait for more than one thing. So we created a wait and capac, and I had the good task to try to figure out how to actually implement them inside the kernel. The kernel was absolutely full. So the only way to implement anything was you had to find space for a few more instructions, all in assembly language here. And the way to do that was to take the panic message that it would print out when it crashed and shorten them down, because every character you took out saved you a byte.
Wow.
in the memory. So then you could fit an instruction in. Yeah, so it was a very different world from today's world in terms of how you had to actually do things. But
can I ask you one thing about you mentioned the risk of working on Unix and signing NDAs and so forth.
mm-hmm.
But as we prepped, maybe there is a positive flip side. You told me, gave me some background on getting TCP experience to a larger group of people that actually worked to TCP's advantage. Can you talk about that a little bit?
Sure. So I built the Unix TCP, but at the same time, or maybe not same time, but within a year, ARPA put out a bunch of more contracts. They had already had contracts with SRI out in California here to implement TCP for the LSI 11, the PDP, the small PDP 11s, which is actually what I used as a basis for writing the TCP for Unix. But there was also a contract with BBN. A guy named Bill Plummer wrote TCP for the PDP-10, and they had contracts with MIT to Dave Clark and his crew to build TCP for things there. So there were a lot of different implementations. And we got at BBN, we got another couple of contracts or work orders to implement another TCP for a bigger Unix system, a VAX, basically, a VAX, which Rob Gerwitz did. And DCEC, which is the Defense Communications Engineering Center, is kind of the halfway house for things that go from ARPA before they get out into the rest of the military.
Okay.
They had a contract to put TCP on PDP 1170 that Mike Wingfield, who used to work on the ARPANET in the early days, was in charge of. So there were a bunch of those kind of implementations going on. Bob Braden did one for the IBM 360. I'm trying to remember who. There is sort of like another. Dave Mills, of course, did one for his LSI 11 fuzzballs. So there were a lot of different contracts. And when I talked with ARPA, with Vint Cerf and Bob Kahn later, I asked them, well, who made that decision? Because the decision was that all of those implementations were publicly available. So you could download the code over the ARPANET. You could get the code and print it out. You could do whatever you wanted with it. And I asked them, who made that decision? And I think it was Vint that said that he and Bob made that decision. That was their decision about how to deal with the TCP implementations, which was very different from the normal thing in government research contracts where everything is locked up and controlled and not really readily available. But the implication of that, which I didn't really experience until 15 years later, was that created a pipeline. So people in universities, networking got to be a really big and popular thing, and all sorts of companies were implementing it. But they all had the same pattern. Xerox had XNS, Novell had NetWare, IBM had SNA. There's a lot of different
DEC had DECnet
version of networking.
Yep.
But all of those, there were obstacles to actually getting at the code or even the documentation. But in contrast, the Unix or the TCP system was freely available. So the university professors picked up on this, and they started using that as the basis for the courses they were giving in networking.
Yep.
So they could download the code, they could put it on machines in their labs, they could have their students come in and build stuff and work on things, and that resulted in wait about 4 years, and all of a sudden the students coming out into industry know how to do things in the TCP world,
right,
and don't have any experience whatsoever in any of the other networking technologies. So the end users, the banks and insurance companies and whatever, they just want it to work.
Sure.
So the easiest solution for them is TCP. If you know how to use TCP, yeah, just do it. Whatever, it doesn't matter to me. I don't care what the protocol is.
Right.
So I believe that made an enormous difference in the ability for TCP to get adopted commercially, and to basically all the others have just been thrown away. They don't exist anymore.
It was a soft coup, as it were, right, through education and exposure, right?
Yeah. There was more to it than that, but education and
Sure.
exposure was a big part of it.
For sure.
That
Can I pick your brain a little bit on kind of the architectural separation decisions? Without going into a tutorial on what NCP was, but the decisions to take what became TCP and separate it out from the IMP code. And then I think that also led to the further partitioning of IP as well. Tell me if I have that right, and expand on that a little bit.
Yeah, I think you have that mostly right. I think there were a couple of things going on. In fact, you should ask Vint when you interview him the same kind of question.
I will.
I've always wondered why TCP put so much mechanism into the computers, the host computers.
Sure.
Because all of the arguments that were made when the ARPANET was being proposed still applied. There were lots of advantages to having it all in one place. That it was easy to control. It was easy to change. It was all run by one company. BBN basically ran the ARPANET and wrote the code for all the IMP software, and made it all happen. So when you put that into the host computer, the mechanisms now are scattered across hundreds or thousands of different implementations, and it becomes much harder to deal with it operationally.
Sure.
So my suspicion is that one of the main reasons was at the time in the ARPANET there was a mechanism called subtype 6, I think it was, but you could actually,
of course, subtype 6.
Subtype
Sorry,
6.
I don't really know that.
You could send a data or a packet into the ARPANET from the host with a type that said, treat this purely as a datagram. Just send it. Don't do anything at all. Just send it out there.
Like no error checking,
Nothing.
Okay.
Just send it. And that's kind of the obvious thing for the TCP/IP world, because it's basically a datagram then,
right?
And that's what you'd like to be able to. That's what the TCP mechanisms are supposed to counteract. Any problems that happen with that datagram along the way, duplicating, reordering, corrupting, whatever, TCP fixes. The problem was that the people running the ARPANET, including DCA, which was running the ARPANET at that time, weren't really comfortable with the notion of all these packets flowing through the net that might actually crash the net. No one really knew. So they were extremely restrictive on whether or not you could use it. So two hosts might literally be allowed to use it for 2 hours one afternoon between just those two machines.
Sure.
Which is a lot different from, hey, we want all the routers that are all scattered around the net now to start using datagrams.
Right.
Yeah. So that kind of fact of life might have motivated putting the mechanisms into the computers, because other people control the computers.
Mm-hmm.
So the initial version of the internet, most of the hosts were actually attached to the ARPANET. The ARPANET provided a virtual circuit service, so anything that went in came out the other end intact. So TCP didn't really have to do a lot of work. because
Sure.
nothing really ever got corrupted or along the way. But that that sort of architectural split had happened,
Mm-hmm.
and we actually had to build some operational tools at one point. We built a thing called the Flakeway, which we used in the context of the ARPANET to make internet traffic unreliable. Because if you were just plugged into the ARPANET, packets would never get lost or duplicated or dropped or anything. So the
So inserting ERA in the ARPANET, like,
well, it wasn't in the ARPANET. We did it by attaching to an Ethernet that was attached to a router to the ARPANET.
Okay.
But it was the best we could do without actually changing the code.
Okay.
In the ARPANET, which we weren't allowed to do that either. It's but the Flakeway made it possible for us to try out the mechanisms that were in TCP and make sure they actually all worked.
Sure.
So that was the kind of the process whereby TCP was getting deployed and tested and made operational. One of the other, I guess I'll go into some of the other operational relevant things here.
Sure.
Because
yep.
We did a lot to make the internet operational by changing things that we could change at the time. But we weren't alone in that. There were other people involved, and one example is the National Bureau of Standards, which is now called NIST.
Right.
They actually created a program which tested TCPs. Mm-hmm. So it was a software program that they built.
So different software implementations for different operating systems.
Yeah, that right. It would test out a TCP to see whether or not it was behaving properly.
Sure.
They also created a program whereby anybody could become certified as a lab qualified to make the tests and issue the certifications that said that yes, this TCP implementation actually does work.
Right.
In addition to that, the procurement arm of the military, the DoD military in the U.S., made it a requirement that any computer system involved in anything that could be hooked to a network had to implement TCP, or the procurement would not be approved. That caused all sorts of people out in the military-industrial complex to sort of wake up and say, "Wait a minute! You mean we have to implement this thing? What is it? How do I do that?" So at BBN, we actually went through the process and we created one of those labs that could do certifications. So we did a lot of consulting work for companies. One of them was one of my cousins that actually called me up one day and said, "Hey, what is this TCP thing? I think you worked on it." I said, "Yeah, I know a little bit about that." But they were all very confused because, for example, somewhere deep down in the specs, it talks about HDLC. And HDLC was a protocol that was developed years before that. And it has an address field in it. And the address field has 8 bits or some large number of bits.
Right.
And he wanted to know, well, how do you test to make sure that it works with all the different addresses and all that kind of stuff? And I looked at it and I said, well, actually, the only thing we ever use is 0 and 1 because it's either this end of the wire or that end of the wire.
Right.
So it was like not an issue whatsoever. And
right.
So the testing tested the things that actually mattered as opposed to every possible thing in the spec. And so we ran a lab for a while that did that for people and got customers that were not normal customers. These were the big military industrial contractors that had some contract that happened to have computers that might happen to have to be connected to the defense data network was the thing that was happening then. So if you think about pipelines, there was another pipeline that was taking the research that ARPA was doing and sending it out into at least the military world. Mm-hmm. And there's a bunch of examples of that. There was a thing called SatNet. The initial internet was the ARPANET, and SatNet provided connectivity to Europe.
Right.
And then people hung local nets, Ethernets mostly, around that, some proteon rings and that kind of thing. But most of the long haul was done either through the ARPANET or through the SATNet. SATNet was satellite-based. It was an Intelsat 4A satellite over the Atlantic. But it was then also transitioned into a pilot program. So there was a thing called MATNet, which was the Mobile Access Terminal Network. MATNet was deployed on the USS Carl Vinson, which was the high-tech aircraft carrier that the military had as a sort of a test bed for new technology. So MATNet was on the USS Carl Vinson, and it was a pilot program basically to see whether or not this kind of technology should be deployed all throughout the Navy. So there were a bunch of those kind of things. In fact, there's had kind of a funny operational story there. We were the contractor responsible for MATNet. And we got a call once. The field service call was needed. There was some problem somewhere, so they wanted all of the people involved, all of the techs from all the different companies involved, and all of the different gear pieces and whatever, to go to the site to debug what the problem was. And the site, of course, was the Carl Vinson. At the time, the Carl Vinson was docked right at Diego Garcia in the Indian Ocean. So we had one of our technicians. And one of our technicians was sent down on a regular airplane to Washington, went to Andrews, and got into a C-5A or something that was heading to Diego Garcia. He had the only seat on the plane which was stuffed full of gear. So he just had this one little seat that was bolted to the floor. So he got to Diego Garcia, and it took hours and hours and hours to get there. And a helicopter took him out to the aircraft carrier, and they did their thing, and figured out what was going on. And it turned out it was some problem with the antenna and the transmitter or something. So it didn't have anything to do with what our stuff was. But when he got to go home, by that time, the Carl Vinson had traveled pretty far out to sea, so they were out of helicopter range. So they actually had to put him in a jet and catapult him off of the carrier to head back to Diego Garcia, to go back in the C-5A, to go back to get home. And I remember he walked back in and said, "I need hazardous duty pay."
I would award that. I would sign off on that, no question. Yep.
But there's an interesting thing that was going on there. It's part of the transition from the research to the operational world. In the research environment, all of the ARPANET sites were at kind of reasonably good places. You went to San Francisco, or you went to Washington, or you went to Boston, whatever. So they were kind of fun places to go to. The military has their sites in really weird places.
Right.
So when we started doing the Defense Data Network, that was a lot of those really weird places that you didn't really want to go to. And, some of them were like places that you had to go in on skis in planes that landed on the snow, and might not be able to get out if you didn't get done in time because, the winter set in or whatever, that kind of notion. That sort of increased the focus. There was always a focus in the ARPANET on remote operations, but that really increased it. It made it less desirable to go to the site than ever before. So we did a bunch of tools to try to address that issue. One of the things that we created was a thing we call the remote data scope. And this took advantage of the fact that in the early days of the ARPANET, UCLA had a contract to basically look at the data for how it was operating and figure out whether it was working or not. These were the days when packet switching was still not known to be a reasonable solution to anything. So they had a bunch of mechanisms that would capture things inside of the IMPs, the ARPANET machines, the switches, and send the data back to UCLA so that they could massage it and try to figure out what was going on.
Does this lead to, is this TCP dump type or log messages, or
not quite yet, but close. That mechanism was still in the IMPs. We found this out, and the imp guys were literally down the hall, so from the gateway guys. So
Sure.
I grabbed one of them and said, hey, did you remember about this? He said, oh yeah, it's still there. We never got around to taking it out. So we decided to use that to create something called a remote data scope. And a remote data scope was, I think it ran on a Spark station, but basically you plugged it in to the console port on an imp, which normally had a Model 33 teletype sitting on it that was just producing occasional bouts of paper and stuff. But
right.
You plug this in, and the software, we put software inside the imp that used that mechanism to UCLA. And instead of sending things to UCLA, it sent them to us. We just changed the address on where the data should be sent. And the remote data scope allowed us to capture the beginning n bytes of packets as they went through. So in particular, if you captured 40 or so bytes, you would get the TCP and IP headers.
Right.
And that was extremely valuable in figuring out what was going on with TCP connections.
Sure.
So we built this thing, and it was actually one of the best spyware tools you could ever imagine, too. But nobody worried about it.
I'm sure it was never used for that, Jack.
Oh, no.
Never.
But that was a tool that we just invented on the fly, and we kept it to ourselves. But it turned out that we ended up showing it to there were some customers who came in who had bought packet nets from us. We had there were lots of clones of the ARPANET in the commercial world.
Sure.
That we were involved with. And some of those customers came in, and we just somehow managed to see this thing being used one day. And they said, we want that. We said, well, it's not a product, it's just a tool we use. And they said, no, we want that. And then they refused to buy any more switches unless they got that. So it ended up becoming a product. But never intended as that. But to me, what that illustrates is there's this enormous gap between the people who are doing the design and research and the people who are actually operating networks. When I went to Oracle, I'll jump ahead again a little bit here. When I went to Oracle, I was in a group that was doing software products for using networks of all kinds.
Right.
But the group I was in also was operating the Oracle internal corporate network, which spanned about 100 plus countries all over the world.
Sure.
So we were not only building products that built the software that used the networks, we were operating the network ourselves. And we also happened to be the ones operating all the data center computers. So there was nobody to point the finger at.
Right.
Whatever the problem was, it was ours. And that kind of linkage between operations and design and research is something that's pretty rare, I think, what I've seen. Usually people split those apart. And as far as I know, no one has yet written the Internet User's Manual. How do you operate an Internet?
Just like there's no, 1-800 call knock, for the internet knock, right?
Right. Well, there used to be, but
used to be. Well, let's talk about that a little bit. So you made this assertion earlier about being the first internet service provider, and you've painted this really interesting. I can create stuff when I need it. I can have my, remote scope software to prevent a truck roll, because a truck roll to San Francisco could be fun, but a truck roll to Diego Garcia ain't going to happen. Right. But you saw the migration from primarily a research environment to a 24/7 operations environment. And I'm sure there's some issues you ran into when the pressure was on to make sure it was working all the time, versus the more relaxed research environment.
Yeah, let me talk a bit about how that all happened. The early days of the internet were very much done by the researchers, and there were a lot of demos of things.
Sure.
And there would be a demo scheduled for Thursday afternoon, so everybody would be there sitting waiting to reboot or whatever you had to do to make the demo work. what happened at one point when especially when SatNet became part of the internet, which actually happened before I got to BBN, but SatNet was part of the internet, and people in the UK, especially, there was a place at University College London. Peter Kirstein was in charge of a group there, and they were linked also out to NDRE, which is the can't remember the name now, but they were linked out to a DoD, UK DoD site out in the Malvern Hills, RSRE, Radar Signals Research Establishment. That's what they called it. That was also a user, and they were trying to do all sorts of stuff, not debugging networking things, but trying to use the network. So they were hooked into the internet through SatNet. So they were the first people that I think of as the real users of the internet, because they actually couldn't do their work unless TCP was working, because they were trying to get from a machine on an Ethernet in London, going through SatNet, through a gateway router to ARPANET, to some machine on the ARPANET, and that's where they were doing their work. So if that path didn't work, they couldn't do anything. That kind of environment, that operational environment, is really in conflict with the research environment that says, okay, demo's done. Let's go and now take it all apart and reboot everything and change all the software, and let's try it again next week. But they both existed at the same time on the internet.
Huh.
So Vint came to me at one point after one of the meetings and said, would you be interested, or would you be willing to take over the gateway project and make it into a 24/7 operational system? And since
can you explain the difference between the IMP and the gateway and the different functions?
Okay, the IMP was the switch that was in the ARPANET. So when you had a host on the ARPANET, a computer on the ARPANET, you plugged it in through a wire to your local IMP port. Each IMP had 4 ports, and then the IMP took responsibility for making all the packets you sent to it get out the other end as you intended. So a virtual circuit
responsibility.
So in effect, inside the IMP was the equivalent of TCP that made
within NCP.
It made all of the things work right. So that's how the IMP worked. The host computers the ARPANET was then connected by another computer, which was a gateway. Today you call it a router, but a gateway plugged into the ARPANET, and it also plugged into a SatNet switch. SatNet switches were called SIMPs, Satellite Internet Message Processor, I guess it's called.
Sure.
So then they were very different in terms of how they worked. But the gateway would pass packets. Well, everybody knows how routers work, I assume. It would take the IP packets that came, or TCP packets that came in at that point, and send them off to the SatNet, and vice versa, to get from the ARPANET node to across the Atlantic to Europe. So I forgot where I was going here.
So Vint asked you if you'd be willing to run with the gateway program.
So we now had this set of people in Europe that were trying to use the internet. And we had these researchers in the US, mostly, some were in Europe, but mostly in the US, that were trying to do all sorts of crazy things. Dave Mills in particular was trying, with his fuzzballs, he was trying new routing protocols and, trying new algorithms and whatever. These were in conflict because things would happen, like if Dave Mills, for example, had a bug, and all of a sudden his machines said they were the best route to everywhere, all the traffic would go to his machine, and nobody could get anything done. And if he or one of his guys wasn't around, there was no way to fix it easily. So that meant that now Vint had the problem that the people in the UK would call up and say, "Hey, the internet's busted." And since they're 3 hours ahead of Washington, that usually happened very early in the morning.
Right.
So being sort of naive and never having operated a network before, I said, "Oh, sure, I'll take that on and see if we can figure out how to make it work 24/7." And that meant that very, very shortly after that, instead of the phone at the ARP office ringing, the UCL guys in the UK would call me to say, "Hey, it's busted and it's not working." So we did a bunch of things, and I remember we got the Gateway Group was basically Bob Hinden, Mike Brescia, and Alan Sheltzer. Those were the three guys that were the primary guys involved in that. And we decided to take advantage of the fact that the ARPANET had been already running for almost 10 years by then, and a lot of mechanism had been created over time to operate the network. The NOC was literally just down the hall. The SATNet world was already being monitored by the NOC, so that when the satellite imps reported that there was some problem on the satellite channel itself, the satellite imps would inform the BBN NOC, the operation center, and BBN NOC would contact Intelsat and say, "Hey, you got a problem. Your satellite channel is degrading." When that first happened, Intelsat basically would say, "Yeah, right. Where are you? Cambridge, Mass. How do you know anything?" and they'd ignore it. But after a little while, they figured out when these guys say that something is about to break, it actually is about to break. So they got a good relationship going after that. But that hadn't happened yet for the internet. So what we did is we took made a bunch of tools and made the internet gateways report back into the NOC in the same way that the ARPANET imps and the satellite simps had been reporting to the NOC. So there were things in the ARPANET called traps, and trap is basically when the imp, the machine, the switch, sees something bad. It might be a failure, or it might just be, "Hey, my buffer capacity is reduced more than it should be," or whatever the programmer puts in and thinks that there's an anomaly. It would report that back to the NOC. And over in the corner of the NOC, there was this printer that would just spew out paper continuously. And that's where all the traps came. And so when you were trying to debug a problem, you would go over to the NOC printer and you'd pull up the paper and kind of scan down. And that would tell you what's been happening over the last 20 minutes or so, which was how people figured out what was going on. So we pushed for the creation of things like SNMP.
Sure.
Because that was the equivalent of traps in the net, in the ARPANET. The SNMP allowed you to actually pull things in from the imps, and you could also go out and query things. The ARPANET imps had a thing called fake host, which was as if it was a real host, but it was actually just in software inside the imp itself.
Sure.
You could connect to it just like you connected to a real host. And it had things in it like DDT, which was a debugger. So with DDT, you could change the code in the imp. You could do anything. It also had things like traffic generators. So you could start a traffic generator that would send packets wherever you wanted them to go to try to test out what was happening. You could change the routing algorithm mechanisms. You could do all sorts of stuff. So we created the notion of fake hosts in the gateways. And put in similar kinds of traffic generators and the like. A lot of those have now appeared in TCP as ports that you can connect to.
Sure.
So there's a lot of ports that do things like character generation and just allow you to exercise the network because those tools had been found invaluable in debugging what was going on in the ARPANET world. And they were equally invaluable in figuring out what's going on in the internet world. What I've noticed just over the last 5 or 10 years is a lot of those tools still exist, but there's also many of them that have degraded because I think people have forgotten why they were there.
Sure.
So that there's like ping, for example, a lot of places, a lot of nodes on the net now don't respond to pings. Ping, by the way, Dave Mills told me what ping actually stands for. It's an acronym.
Is it Packet Internet Groper?
Yes, it's Packet Internet Groper.
Thank you. Yep.
I don't know whether Dave invented that or someone else, but that's he told me that long ago.
Well, the dual use, the sonar analogy and the retronym acronym, whenever it was really acronymized, it's very descriptive.
Yeah, it's very descriptive, but also very useful. So a lot of those kind of tools that were used in the ARPANET, we tried to push into the internet, and we got a lot of them in there. But I get the sense that there are a lot of people who don't understand why they're there, especially people who don't have anything really to do with operations because they don't understand what they're used for, and no one's written the how do you operate an internet book.
I got a project for you, Jack.
Well, I actually wrote that at one point.
Okay.
We did lots of networking for government clients as well as commercial. And there was one government client that basically had exactly that question. It says, where's the manual for how to operate this thing? And we said, well, there isn't really any. So they said, well, can you write one? So I wrote this thing that was probably, I don't know, half an inch of paper or whatever. And it was called something like Managing Large Network Systems. And it's disappeared into the bowels of the government. So I have no idea where it can be found or anything like that. But I still remember.
You don't have a floppy anywhere
No,
that might have it. Yeah.
It was one of those things that was they owned it, so it had to go to them.
Sure.
And it's probably in DTIC somewhere, but DTIC is at the Defense Technical Information Center. It's a good source of lots of that kind of stuff.
Right.
But the principles that were in there were things like things that I had noticed by watching not only myself but the engineers that were involved in this debugging problems. And so somebody would call up with a problem, or you'd somehow find out a problem, and you'd go look and use all these tools to figure it out. In fact, one of the very, very early ones of those that I can remember is one of the guys was Mike Brescia, that he was working on the internet stuff, and he took it. He actually also came from Lick's group at MIT. I worked with him at MIT, so he joined our group at BBN, and he took over sort of. He was the father or the mother of the internet as it worked then, and he'd watch over it every day. He was very maternal about it.
Wow.
So he was using these tools, and at one point he was getting all sorts of checksum errors from some gateway somewhere out there, and so that was unusual. So he started poking around to figure out what was going on, and he noticed that the gateway errors were all coming from one particular source address. So that meant it probably wasn't a bad cable or a bad connector or any of that kind of stuff. So it was one source address. So he used the Datascope tool to capture the packets, and he figured out what host it was coming from. And he noticed that the checksums were failing because 2 of the bytes in the address field were swapped.
Huh.
So he looked up the computer in the Network Information Center, and the computer was a PDP-11, and we had all worked on those, and we knew that was which order the bytes are in is always a problem on PDP-11s. So he looked at the packets, and then he sent off an email. He found out who was the technical contact at that particular machine, and he sent an email to that person, figuring that that's probably the person who's actually involved in whatever's going on there. And the email said something like, your IP packets are malformed. The 2 address bytes in the high order bit need to be swapped, whatever. He said how to fix it. And so he sent this mail out, and an hour or 2 later, he got back an answer. It said, hey, that's right. Thanks very much. You fixed it. So then about an hour or 2 later after that, he got back another email. How the hell did you know that? Because he knew that we were in Cambridge, Mass, and he was in Wisconsin or somewhere. I don't know. And it was like remote debugging. was how you did things.
Yeah.
And
You just can't get in a car or plane, right? To go in and troubleshoot it. Yep.
So I ran into that same kind of situation again when I went to Oracle. People would the guys who were running our NOC there would when they had some problem they couldn't figure out, they would say, "Hey, can you come in and look and take a look at this?" So I went in and I looked at it, and we solved a bunch of problems that way. But one of the times, one of the problems that I had, and in fact, I think all of the internet technical people have had, is that they don't look too much outside the technology that they're working on. So, for example, I knew that things like databases existed, but I had never actually worked with one, or didn't really know how they worked or what they did or why they were useful or whatever. But when I got to Oracle, everybody there knew a lot more about databases than I did. And I knew about networking, but everybody knew about databases. And databases were the things that basically all the customers focused on. They didn't move packets, they moved data. So the one afternoon, one of the guys who was in our group and knew a lot about databases, and I went with him, and we sat down at a Spark station, I think it was, in our NOC, and we started playing with scripts, just Unix shell scripts, using SNMP get to probe the routers that were out in the world. And within about 3 or 4 hours, we just sat there, and I would say, well, here's all this data, and here's how we can get it. And so you type in literally one line of text, and all of a sudden you start getting SNMP messages from some particular gateway out there.
Right.
And so he said, oh, well, we can just extend that script a little bit, and we can put this into it, and that'll shove every line into a database. So we had every SNMP report that came in just getting put into a database. Then he kind of took over and said, oh, well, okay, now we just do this. And he starts typing madly at the console. And within about an hour or two, we had a rolling chart on one of the big screens in the NOC showing packet transport and packet loss data for routers on our trans-Pacific link that was up in real time. So it would scroll past, kind of like a heart monitor you see in hospitals. So we could now actually see exactly what was going on in the net because of the fact that he knew all about how to manipulate the data, and I knew how to get the data out of the routers and get it into the database. And coupling those two technologies together, we made a tool that was much better than anything I had ever seen in a network company's products, including the ones that I worked on. So it was just a sort of a revelation that, God, it's just data. So what's coming out of the network is data, and we know how to manipulate and process and present and make decisions on data. So that linkage made a huge difference. That actually came to be very useful. Since we were in charge of all the stuff, there wasn't anybody to point the fingers at. So we would get calls, and we got a call one time from I think it was somebody in Singapore, and every week, I think it was, they had to send some big report back to headquarters, and they would do this, but it all of a sudden it was taking like 2 or 3 times as long as it used to. So they were worried they weren't going to be able to get it there by the deadline. And they said, the network is broken. What's going on? And so we said, okay, we'll take a look at that. And so we used all these tools, and we found out that what was happening was there were occasionally, on the trans-Pacific links especially, there were occasional glitches. And when a glitch started on this rolling monitor that you could see on the wall, before a glitch, we'd be getting, I don't know, I'll just pick a number, let's say 10 kilobits per second throughput. And then there'd be a glitch, and then things would, be bad for a minute or two. And then things would settle back down. But when they settled back down, it was only 5 kilobits per second.
Mm.
It was half of what it had been before. And nobody was complaining. As far as all of the switches were involved, everything was fine. Nothing was bad. So we started figuring out, well, what's going on here. And because we had the ability to capture the packets, and we could go in and do SNMP gets on machines or whatever, we figured out that what was happening was the TCP implementation in one of the machines. I don't remember which end it was, but one of the machines had essentially a bug in the TCP implementation that would, when the glitch happened, it would, of course, have to retransmit. And then when it settled down again, the timers weren't quite back to where they should be. So every packet was getting sent twice.
Huh.
And at the other end, every packet was getting received twice, and one of them was being thrown away.
Right.
But everybody was happy. Except the user who said, it's taking too long. What's going on here? It's busted. We probably should also have been unhappy that this very expensive trans-Pacific link was now being half wasted because of that retransmission thing. So we fixed that, but it just revealed to me the kind of issue that you get into operationally when you start looking at what's going on. TCP is wonderful at correcting errors and keeping everything flowing, but it's also wonderful at hiding problems. So things that aren't working, it doesn't care. It'll just keep getting through. So the operation tools that allow you to actually look at what's going on, not just in the switches, but all the way out to the end users who are sitting there trying to actually do their work, whatever it is, that has to somehow be factored into the equation. And over time, what I've seen is it used to be that the operations center operated everything. Now it seems like there are operation centers, and not only are there way too many of them scattered around the world, but they are also very insulated to just their own little piece of the puzzle. Mm-hmm. And they don't know what's going on outside, and they just think that everything, as long as none of their equipment is complaining about problems, everything is okay. So it's a system level issue, not a piece level issue.
And for another time, that system level analysis and trade-offs between what can help me scale versus what obfuscates or hides pieces of the problem, so I don't see all the necessary inputs in one place. That's a bigger conversation for sure.
Oh yeah, absolutely. Yeah, there was one of the things that you asked about before was what ARPA should do, or what somebody like ARPA should do if they had ARPA style funding for something.
Today, if there was one thing, from the to-do list that you could do, yeah.
It's the same one that was there in 1983. 1983, Bob Kahn and I were talking about stuff and about operations stuff, because Bob Kahn was the guy who told me that we had to make it possible for people to build gateway, build routers that weren't all BBN. So he mandated that we figure out how to split the world apart so that there can be lots of different vendors involved in it. And so I sat down with him one day and I said, hey, operationally, this is really a problem. And we ended up creating a thing called automated network management. And the notion of automated network management was that when you look at what real people do, the engineers, when they debug things, there's a lot of different things they do. And in particular, they have a thing that I used to call an anchor host. An anchor host is merely a host out there at the user's site that the engineer who's trying to debug the problem really understands. So it's something that they know how it works. They can put their software on it. They can run tests from it. It's the equivalent of the fake host in the ARPANET imps. It's the machine that that you can work with, and you can trust what it's doing, and what it's doing. And more importantly, you remember how it used to work when it worked. So you know how it worked when it was working, and now you can see how it works now. And figure out what the difference is and then debug the problem there. So automated network management was intended to try to take that kind of a notion. And at the time, the buzzword in the AI world was expert system.
Sure.
And I had done an expert system at MIT with Licklider to figure out how to decode handset Morse code. So I kind of knew sort of how that stuff worked. I have no idea how today's AI worked, but that world I knew. But in 1983, the idea was to build an expert system that would replicate the kind of things that people did, and try to automate a lot of that kind of activity. All of the analysis and the trying out different experimental things and all that kind of stuff. So that project got funded by ARPA. But unfortunately, what happened is one of those things that it's one of those Deus ex machina kind of events. BBN reorganized, and the researchy stuff got put in one part, and the operational stuff got put in a different part. And I went into the operational stuff because that's where I was interested, and the automated network management went into the researchy stuff because that's what they were interested in. And so we lost the linkage between.
Sure.
So I don't know whatever happened with A&M, but it didn't do what we had envisioned. But as far as I know, that kind of mechanism, it's probably even worse now. I mean, does anybody understand how people actually debug problems in the internet? My
divide and conquer is like they look at pieces of the problem, but it really is hard to get the global view.
Yeah, well, and especially the other thing that matters is getting at it from the customer's view. I don't mean the customer in the sense of the ISP you're hooked to, but the customer in the sense of the human who's sitting there actually trying to do something. Getting back to Licklider's vision, it's the computers and interconnected computers that help people do everything people do. So the question is, how do you help people do what they're trying to do? So you have to go out to where those people are and understand their experience. There's been many cases I've heard of where the user says it doesn't work, and no matter who you call, they say everything's fine.
Looks fine. Trouble all clear through here.
Yeah, everything's clear here. Everything's working fine here. It must be somewhere else.
Right.
So the only option you have is to go somewhere else. I thought it was fascinating. I read an article, I don't know, last year sometime, that the latest high bandwidth addition to the internet is 10-wheeler trucks.
Right. High throughput.
High throughput. Delay is not so wonderful, but
right.
And the cloud providers, that's how they move data. So they don't shove it through the internet. They use an alternate mechanism.
Well, all sorts of use cases, right? There's we didn't touch on half of what we prepped for, and we're about to go around the final curve here. But let me ask you, for folks that are listening in ops roles and related roles, do you have any nuggets of, besides the things that you've hinted at through the course of the conversation today, like what are some key learnings that you had that have really you've taken away from, moving from research to operations 24/7, things along those lines? Give me one or two of those, what you'd love people to take away from that.
Okay, I think, well, the main one, of course, is what I've talked about, which is, take a look outside your world, that kind of thing. But I think one of the things I realized was you should never ignore or forget glitches.
Okay.
Because things happen all the time. And you should at least remember that they happened, because they're going to happen again. And so, the standard thing, I do it with my own computer all the time. Something bad happens, and I know that if I unplug it and plug it back in, it'll probably be fine again.
But you didn't capture any data, and you didn't really resolve anything.
I didn't really resolve anything. I just got it working again. But that's the main thing, is just at least remember that it happened. It's an interesting. There's another distinction between research and operations. If you're a researcher person, when something bad happens, you immediately want to rip the machine apart and figure it out. If you're an operational person and something bad happens, you immediately want to get your system back up and running, and those guys can go figure it out later.
Yeah, restore service. I've got customers.
Yeah, I got customers. You got to restore that service. So you got to remember those two aspects of it, and somehow balance them out. You need both of those to really make things work. But
we'll have to find a way to have you back and cover the rest of our outline and more. We didn't even get to talk about EGP or differentiated services and type of service, class of service, but we'll leave it for another time.
Okay.
You're out there on certain things, like, I've seen some of your presentations at other conferences, the ARPANET in 2022. You forwarded some great, blog responses. Do you still publish stuff regularly? What do you do? Do you have a presence out there that you can point people to?
Well, not necessarily point people to, but there a lot of the things that I've been talking about. I've discussed over literally the last 10 years.
Right.
There's a mailing list at ISOC, a forum basically called Internet-History.
Okay.
And it's hosted by ISOC, and if you they have archives there. So if you go to the archives, you'll probably find a lot of the things that I've said today, even discussed over the last 10 years or so in those archives. I'm actually working on putting it all together into a book, which Vint Cerf keeps yelling at me to say, get it done. That's in progress, but that's the Internet History Group is the place where you'll find a lot of the existing stuff, and it's still quite active, and there's still people who are actually involved back in the 80s are still there. So it's very much a source of information about what actually happened, and what the real issues were back then, and so on.
That's a great pointer, and I'll make sure it gets in the show notes. And I'm probably going to spend way too much time on that now. Thanks a lot, Jack.
Well, here's a challenge for you. I've been wondering if it's possible to take one of the new AI-ish things and point it at that list, and just the archives, and get it to read in all that stuff. And then I want to ask it even simple little things like, can you tell me all the things I said?
Sure. That
should be doable.
That should be doable, and I'll give the famous Total Network Operations No prize to the first listener that takes up that challenge. You all know how to reach me. So, Jack, I can't tell you how enjoyable this has been. Prepping and talking to you today. I definitely count it as basically a highlight of my career, and this history is really important. If you can't remember the past, you will repeat it, just like your comment on glitches and crashes. Remember that it happened, because it's going to happen again. You want to know how to work around it next time, and better and more quickly next time. So, Jax, thank you so much.
Welcome. Glad it could help.
Good. And to our listeners, all you operators out there, thank you so much for spending time with us today in Total Network Operations. We will talk to you again soon.